Thank you very much for the organizers of the. This is not the usual audience I'm used to. I'm a physicist, but I will try to be as rigorous as possible. And today I'm going to talk about quantum groups as global symmetries based on works that are already out.
Can you be also louder?
Yes.
Yeah.
Today I'm going to talk about quantum groups as global symmetries based on the two works that are already out and some upcoming work with my collaborators Barak Gabay, Victor Garbenko, Jashin Kiao, and Bernardo Zam, who is in the audience and who will be giving a second part of the talk on Thursday. Okay, so why do we study quantum groups? We know in physics that the concept of symmetries is very important. They have proven to be extremely useful. And usually what we study from the textbooks is that the symmetries form a group, either a discrete group, or if it's continuous, then it's a Lie group. And they act on local objects, on local operators. But then people have discovered supersymmetry, and more recently, people have discovered higher form symmetries, non-invertible symmetries, and new types of symmetries that do not form a group. So in principle, we would like to address a question: what are the most general symmetries in quantum systems? Of course, answering this question is very hard. So we take an existing mathematical object called a quantum group. I will explain what I mean by this later. And we study quantum field theories, conformal field theories in particular, with such a quantum group as a global internal symmetry. And how I'm going to address this question, I will start with explaining what do I mean by a quantum group. Then I will quickly review the standard formalism for the symmetries that is used nowadays in the physics literature. And then I will explain what are the general constraints from the quantum group imposed on the quantum field theory. Then I will discuss a particular example of a conformal field theory with such a symmetry. And in the end, I will mention some non-integrable systems with such a symmetry. All right, so for me, the quantum group is a quantization of the universal enveloping algebra of SL2. So let us recall the commutation relations of the usual SL2. Yeah, so I'm focusing on the simplest, for me, the simplest quantum group, the quantization of SL2. But in principle, this construction can be done for SLN or some other algebras. So the commutation relations of SL2 are written up there. So let me remind you, so the generator H is the Cartan generator, and the E and F are raising and lowering generators in the algebra. So I think of the quantum group UQ of SL2 as a deformation of these commutation relations. In particular, the commutation relation between E and F is deformed in this way. And the parameter Q is a complex number. And in the limit Q to 1, one can recover the standard SL2 commutation relations. The representation theory of such an algebra for generic Q is very similar to those of just SL2. The representations are labeled by half-integer spin, and they are 2L plus 1 dimensional. L is the spin. For Q a root of unity, the representation become more complicated, but let's for now focus on generic Q. And we want to act on the tensor product of representations. And to do that, we have to introduce a coproduct. And here we do this. And the difference between the coproduct for UQ of SL2 and just SL2 is the appearance of these factors in red here. Just for SL2, it would be just 1. Instead, for the quantum group, it's different from one. And historically, such an object was introduced by the people who studied quantum integrable systems on the spin chains, and was later formalized by Greenfield and G. Right, so now let me review briefly the standard formalism which people are using for describing the symmetries. Let me review it for the usual symmetries, and we will apply it for the quantum group later. So for the usual symmetries, when we act on some operator with some generator X of symmetry, we surround this operator by the surface and integrate the current over this surface. And then one can shrink this surface and obtain an action on operator O. And the conservation of the current means that the surface is topological and one can shrink it and extend it as much as he wants. From now on, I will focus only on 2 dimensions, so that this surface is just a line. So, and when one wants to act on 2 operators in the theory, then one has to surround these both operators with the surface. And by shrinking this contour, one gets the usual coproduct for the usual symmetry generators. This formalism also tells that when one has 2 contours, 2 lines, one can fuse them, and this would represent the multiplication of generators. And this will define the algebraic structure of the symmetry. And in principle, one can now think about the symmetries only as topological lines and forget about the currents that one has to integrate. For example, discrete symmetries do not have a current which you can integrate, but you can still associate each element of the discrete group with such a topological line. In principle, such a formalism doesn't require for any group element to have an inverse element, and one can construct so-called non-invertible symmetries. So let us now try to apply this formalism to the UQ of SL2, but we need to formulate what do we mean by the quantum group symmetry. So we want UQ of SL2 to be a global internal symmetry, which means the following. The generators have to commute with the Hamiltonian, and they have to commute with all the space-time symmetries. In particular, in the case of the CFT, they will commute with all Virasoro generators. The operators in our quantum field theory have to transform linearly under the quantum group. So the operators live in some representation of this quantum group, and they carry an index. And the correlation functions satisfy UQ of SL2 ordered entities. Now I will explain in more details. So as I said, the operators transform in some representations under the quantum group, and each operator has an operator OI has an index L, which tells in which representation it lives, and M is like a projection of the spin. It labels the state in the representations. So H acts as a diagonal element. It does not change the M, and E and F act as a raising generator and lowering generators with a certain matrix elements. And this is the action on a single operator. And formally, the action on two operators will be given by a coproduct of any element. And the action on 3 and 4 and so on operators will be given also by applying coproduct several times. So the word identities, generically, one would write as an action of some symmetry generator on the set of operators inside the correlation function. And this has to be 0 for any element from the quantum group. The action of H is simple because H or Q to the H is a U1 subgroup. So it just gives a U1 charge conservation. So it means that the sum of M1, M2, and so on has to be 0 of all the operators inside the correlation function. And to get a non-trivial word identity, one can act with a generator F, for example, on the set of operators for which the sum of Mi is equal to 1. Then action on F will, there will be several terms. In each term, it will subtract 1 from any Mi, such that for each term, this conservation will still hold. But the action of F would yield this coefficients FLM, and this will give us the non-trivial word identities. So this is the generic constraint. Let us now see how we can think of the operators. So before it was just a formal construction. So first of all, let us see if the operators can still be local with such constraints. Let us assume that the operators are local, such that the commutator is 0. Let us act on this commutator with, for example, generator E. And then we obtain something in the right-hand side, which is not 0, exactly because of this factor of Q to the minus H, which is coming from the coproduct. And generically, this right-hand side is non-zero. So we cannot have a quantum field theory of local operators that transform under this quantum group symmetry. So they have to be non-local. And the mild way in which they can be non-local is when we attach a topological line to every operator in our theory. And this happens to be enough. So we don't need to introduce more non-locality. And as I said, these are topological lines and one can freely move them around. And in particular, the ordering of these topological lines will give us the ordering of operators inside the correlation functions. And for example, on this slide, you can see the different possible orderings. Let us now try to...
There's an infinite number of these, right? Not just 3.
Sorry, say it again.
There's an infinite number of possible. You can always sort of wind it 20 times.
Yes, exactly. Yeah. This would mean you will go on the next sheet of your Riemann surface. So let us now try to introduce the symmetry generator, which would act on these operators. And as one can see from this picture, just a symmetry generator, which would be an integral of the local current, cannot satisfy the correct quantum group coproduct because it just gives the usual coproduct. So one has to modify it in some way. And the modification that we suggest is to integrate this current, but the current itself has to be attached to additional line. In this case, it would be a U1 line. And now, when one shrinks this contour surrounding two operators, one will have this remnant U1 line, which would surround the second operator. And by shrinking this U1 line, it would give exactly the factor which is the same as action of Q to the H. So such a picture reproduces the correct UQ of SL2 coproduct for F, but one can also draw a similar picture for the generator E. Okay. And now, since the operators themselves are non-local, one can ask what happens when we permute them. And these operators have to satisfy the so-called braid locality condition, so that when one permutes two operators in the correlation function, there is a factor appearing here. And these factors are the matrix elements of the universal R matrix. There is a concrete formula for this R matrix. And by evaluating it in given representations of spin Lj, Li, one gets these elements. This R matrix satisfies the Young-Baxter equation. And if one draws a picture for the formula above, it would look like this. So in this picture, we exchange the ordering of red line and blue line, and we get this factor. So now we know how the operators look like in our theory. We know how the coproduct looks like. Let us now ask ourselves what would be the solution for the word identities that we have. What would be the correlation functions? So the two-point correlation function has to be, so yeah, once we normalize the operators, as I said in the beginning, then the correlation function, the two-point correlation function will be proportional to the quantum Clebsch-Gordon coefficient. And the coordinate dependence for generic QFT can be difficult, but as we will see later, for the CFT, it will become just the usual scaling dependence. And for the three-point correlation function, so we have the, thematically speaking, we have the tensor product of three representations. So we have to first take the Clebsch-Gordon coefficient in the product between the first two, and then with the third one, and then we get the product of two Clebsch-Gordon coefficients. And for the higher point correlation functions, one would have several trivial representations appearing, and one will have to sum over all invariant tensors in this case. Okay, so to sum up the results for the quantum field theory before going to the CFT, we are saying that quantum group symmetry charges have to be non-local. They are attached to, they have this U1 line attached to the current. The usually local operators in quantum field theory have to be replaced with the operators attached to topological lines. And the permutation of these operators will satisfy the braid locality condition. However, the constraints on correlation functions are in principle as powerful as for the usual symmetries, as for SU2, for example. So the word identities leave us with the same number of degrees of freedom as the SU2 word identities. Let us now talk about the specific example which we studied. This example arises from some spin chains. There were some examples already known in the literature. For example, there is a famous paper by Pascal and Salor where they describe the open spin chain. But this open spin chain with the UQ of SL2 symmetry in the continuum limit would flow to a boundary CFT. However, we are interested in the bulk operators. So we are considering another example, which arises from the spin chain written in this reference. And on Thursday, Bernardo will talk more about the spin chain formulation of this. However, right now, I would like to focus on the continuum limit. In the continuum limit, it becomes a CFT with the partition function given here. So let us look at this formula. This formula has the two L+1 degeneracies that corresponds to the quantum group representations. So we have operators that have the same energy and have to be transformed into each other by the quantum group. And the conformal weights are encoded into these characters. It's a standard notation. Okay. And in principle, this theory is not diagonal. It has chiral operators, for example, for r equal to 1. There will be a chiral subsector. But it also has operators which have both chiral and non-chiral components. And
this partition function counts what? It does count. So this counts the disorder fields, right? The fields with the defect lines already attached. It's not the partition function of just the local fields.
Yeah, exactly.
You can see from the weights of left and right.
And the parametrization that we are using is coming from the lattice. We are representing parameter Q in this form, where mu is the real number greater than 0. And then the central charge of this CFT will be given by this formula. And in particular, when mu goes to infinity, this central charge goes to 1. Q goes to -1. And when Q goes to -1, it's almost the same as Q going to 1 up to some signs. So we say that we recover the standard. I didn't explain the spin chain, but it would become just the XXX spin chain with SU2 symmetry.
So is it possible to say what are the characters? What are the...
Sorry, can you repeat?
What are the characters in the partition function?
Yes, these are the standard characters of the degenerate Virasoro representations with this central charge.
The characters of symbols, right?
Sorry?
Symbols, irreducible. Reducible Virasoro representations or cuts.
They are from the cuts table. So the primary operators will be from the cuts.
Yeah, but the Verma module or Pegen-Fuchs module has singular vectors. So
so we subtract the singular vectors.
But spin chain, you mean like it's a periodic or with a twist, XXZ? Usual XXZ spin chain.
Yeah, so in the bulk, it's like an XXZ, but then there is an additional term, which I hope will be more clear from the Thursday's talk, but I can explain to you like after the talk.
Twist. It's not just twisted?
It's not just twist, it's a bit more complicated. Okay, so the conformal dimensions of the primary operators are given by this H R, S from the cuts table with degeneracies to L+1. And in particular, one can notice that they have a non-zero space-time spin, which is also not an integer, not a half integer. And it is compatible with saying that the operators have to be non-local.
Sorry, but your Hamiltonian is non-local, right?
Yeah, so this additional term, it will become,
translation, right?
Yes, it will be non-local.
Yes.
And in terms of CFT, we can formulate everything in terms of the OPE. When we write the OPE between two operators, we are saying that the result has to be proportional to the Clebsch-Gordon coefficient, quantum Clebsch-Gordon coefficient, times the OPE coefficient. But now this Cijk, it does not depend on Mi, Mj, and Mk anymore. And it contains the dynamical information. So by taking this OPE of the two operators, we can say what is the two-point function. So the difference between this formula and the one that I showed before is that we now know the coordinate dependence. And for the three-point function as well, there will be these OPE coefficients appearing, and the standard CFT coordinate dependence for the three-point function. And for the four-point functions, one would have several invariant tensors appearing. So the different expansion will be related to each other by the 6J symbol. And so the crossing in the CFT will have the 6J symbol there will be 6J symbol as a crossing kernel. So imposing these constraints, we were able to solve the XXZQ CFT. So we found all the OPE coefficients. Okay, I do not have enough time to explain how exactly we did it. But if you're interested, I can explain after the talk. We also studied what happens for Q a root of unity, because I remind you that Q was on the unit circle. And when parameter mu hits an integer, then Q becomes a root of unity. And in this case, the CFT becomes logarithmic, and nevertheless, there are the unitary subsectors with the local operators. Okay, so I'm close to the end of my talk, and let me now present you some fun slides. So imagine doing an experiment, and imagine you're an experimentalist and you want to detect the quantum group symmetry. How would you distinguish it from just the SU2 symmetry? So suppose that you're doing an experiment and you can measure correlation functions, and you know already that your theory has U1 symmetry and your energy levels are 2L+1 degenerate. And in particular, you measured that there are triplets with the same energy in your theory, which have U1 charges +1, 0, and -1. So at this point, the natural guess would be to say that these degeneracies are explained by SU2 symmetry. However, from the SU2 symmetry, you would also know that the three-point functions will, of the triplets will be proportional to the epsilon ijk, the antisymmetric tensor, which means that the three-point function of operators with charge 0, 0, 0 would vanish. However, the UQ of SL2 prediction tells us that it is proportional to the quantum 3J symbol, and it is non-zero. And if you can measure this three-point function, you can distinguish the SU2 and UQFS. And the last interesting piece of the information that I wanted to tell you is the following. So historically, these quantum groups, as I said, they appeared in the literature of integrable systems. However, the way how we formulated these symmetries, we did not rely on integrability in any way. So the natural question that we had, can these symmetries also exist in non-integrable systems? And to answer these questions, we took the Hamiltonian, the original Hamiltonian, which I was referring to and which Bernardo will explain on Thursday, of the spin chain, it's this H. And then we came up with a certain deformation of this Hamiltonian, which still preserves the quantum group symmetry. And then we studied the energy levels of this Hamiltonian numerically. And what we observed is that as we take this deformation parameter lambda being equal to 0, which means we end up with just the original Hamiltonian, then the energy states, they form this Poisson distribution. And as it is believed, it means that the theory is integrable. However,
what are the axes?
Yes, so this is the level spacing distribution. So S is the difference of the nearest neighbor energy states, and P is the probability of the states. So when we turn on this deformation, when we take lambda to be some non-zero value, then we observe clearly different behavior of the level spacing distribution. This red one is a formula for the so-called Wigner distribution, and we see that our numerical data is very well approximated by this Wigner distribution. And in this business of chaotic systems, when people see such a distribution, they say, oh, then there is a level repulsion in the system, and which means that the theory is chaotic. So we would like to conclude that such a quantum group symmetry can also exist in the chaotic systems. It does not rely on integrability in this formulation. So let me now summarize. The quantum group symmetry exists both on the lattice and in the continuum. We will hear more about the lattice later. It provides constraints on quantum field theory, in particular on conformal field theory, operators and correlation functions. It provides some new properties for these topological lines, which I drew before. In general, the theory of non-local charges is promising and underdeveloped branch of generalized symmetries, and it would be interesting to see developments in this direction. Thank you very much.
Other questions?
So how is integrability and Poisson distribution of energy gets related?
Yeah, so the standard law in this integrable versus chaotic systems is that you study the energy spacing distribution, and if your distribution resembles this blue curve, the Poisson distribution, then people say that it is integrable. And when it resembles this red curve, then this is chaotic.
So it's somehow that in an integrable system, the energy levels do not talk to each other. So
yeah, exactly. Yeah.
Yeah.
So can we say that so this is a manifestation that the additional quantum group symmetry is a symmetry, but it does not provide an infinite number of
Yeah, exactly.
so it is similar to a non-integrable model.
Yeah, like SU2. You can have SU2
You
symmetry.
can have SU2, but yeah, and the fact that you can solve it is because it's integrable.
Yes, yes. The CFT that I was mentioning before, it was coming from this Hamiltonian only without this deformation term. And we were able to solve it because it is integrable.
Yeah.
And it is like you use the fact that your correlation function satisfies BPZ equation. I mean, because your correlation function.
Yes, they do. Yes, yes. We impose the crossing and basically.
So in your presentation, you insisted on the U1 symmetry, but then in the example of you had this cuts table, does that have a U1 current?
Yes, it. Yes, I think this index R is the U1 quantum number.
Okay, but it's not necessarily a weight 1,0 field, yes?
Yes, that's correct. Yeah, so we don't have the currents in the spectrum, if you're asking this. So this might appear surprising, but
you want to integrate it.
Yeah.
Okay.
But we still observe the degeneracies in the spectrum, and we say that, okay, well, since it is non-local Hamiltonian, maybe it's okay to not to expect to see the currents in the spectrum.
What is the continuous interpretation of the TTR equals RTT equation of integral systems? I mean, before you've had like this triple R gives the fact that you can interchange the order of your lines.
Yes.
Do you have any interpretation of
Yes, so you can draw the picture corresponding to this equation, and this will just correspond to different like braiding of your lines.
And so the TTR equation with the transfer matrix, which we usually use in, I mean, discrete systems, does it have an equivalent or?
Yeah, so this is the equation for the integrable systems. But here we try to formulate everything without relying on integrability. So for us, the Young-Baxter equation is just a way of how you can braid the lines.
Questions? Okay, in the case, let's thank Alexandr.